Okay, welcome everybody, and I'm going to welcome to the presentation on BlackLight power. Glad to have you, and glad to participate in Emerald's forum here. I'm going to cover some technology. We've been working predominantly on engineering. It's been a very successful progression of moving the technology from theory to the analytical, to power production, and then engineering a system that can be used in a competitive manner with fire. It's been an enormous amount of work, but it's been very successful. So I'll go through various facets of that in the presentation today. So what we're working on is a new form of energy where we take the electron of the hydrogen atom and we collapse that down to a new chemical energy state called a hydrino. It's Latin for small hydrogen. It means the electron's closer to the proton. So if you're thinking the hydrogen atom in terms of a building, in terms of a spatial separation, the electron would be at the top of the Empire State Building. The proton, the positive charge binding particle, would be at the ground floor or street level, and there'd be empty space in between. And there's electrostatic traction between the negative and positive oppositely charged particles. What we're doing is letting that electron move closer to the proton and releasing energy. The typical energies involved are enormous compared to chemical energies. It's on the order of 200 times the energy of burning hydrogen. So we would move it, say, from the top floor down to 1/4 that distance to the peak, which would be about the 25th floor. So we're moving it to 1/4 the traditional atomic size of hydrogen, releasing enormous amount of energy. So the challenge is, how do you move that electron to the lower state in a very, very fast manner, so not only you get a lot of energy, but you get a lot of power. So we can compete in global energy markets, which are shown here. And needless to say, the potential for producing power in a clean, effective, cost-effective way would address very, very large markets and very large necessity in terms of making clean, cheap power in various applications for stationary and mode of transportation, for example. Those markets are growing, and traditional energy sources like wind and solar are very, very inadequate to meet any substantial amount of those demands in the future. So we're addressing essentially the entire gamut of market. There's no niche market in this. This is the entire energy market that we're talking about. We have a number of technologies we've created over the years, and ever more advancing them towards getting commercial devices. About this time last year, I was presenting on a tremendous breakthrough that we had achieved, and that is to create an enormous amounts of power. We'd always made a lot of energy, but now we're making extremely, extremely high power densities, and we've had the technology validated, and it fits in with some of the licenses we have. We have about 8.25 billion watts we've licensed to utilities. We can certainly do service those types of markets, but I'm going to talk about a fundamental new way that we're producing power that can address all markets, including mode of market, not just central gen market. So the cost is projected to be extraordinarily inexpensive compared to traditional energy sources. We could be as low as 10% to even 1% of traditional energy costs in terms of producing electricity at the site. And that would alleviate any necessity for transmission. So just to give you a quick reframe, I'll reframe just off the technology for a second and just take a little break here in terms of how this works. Fundamentally, the premise was that the physical laws that govern our modern society, that is transmission of electricity, lasers, radio communication, cable, electric power generation, transmission, all motive systems, they're predicated on classical physical laws. And then there's another theory that says the universe is not physical at all. It's purely mathematical. The challenge is that there's nothing in between. So if you transition from the mathematical to the physical world, what would apply in between? And the mathematical world doesn't give you a real physical picture of how things work. It's more or less an algorithmic approach, and has failed in a number of very, very important instances. For example, 90% of the mass of the universe is yet unidentified. This approach solves everything from subatomic particle masses all the way to predicting the acceleration and expansion of cosmos, and unifies physical laws on all scales. It overthrows the fundamental equation of quantum mechanics, and for that reason it's been quite controversial, but the results speak for themselves. They're extraordinarily accurate without any algorithmic approach. This is pure physics applied to a mechanism of what the atom is and how the atom behaves, and it predicts this new energy source. So shown here are examples where molecules can be shown to be solved in analytical expression. That's impossible with current theory. It uses huge computer algorithms and adjustable parameters, and the results from this is absolutely perfect in all aspects towards observations. As a comparison of its utility compared to existing theory, on the left you can see the predicted and experimental numbers. There's perfect agreement to limit of measurement, and you can see the latest state-of-the-art quantum mechanical approach is purely random and shotgun. And then if a picture is worth 1,000 words, this is showing you what the analytical expression is and what a real-world image of what a molecule, particularly pentacene, is shown here, and you can see all the different atoms here, the hydrogen electrons of the hydrogen atoms and the carbon atoms, and there's a perfect agreement with the geometrical parameters and the energy parameters with these solutions. The current theory says you can't even make images. The electron doesn't even really exist. It's purely mathematical. So you can see it's quite real and quite imageable. So what that theory does is predict a new energy process. You can have the hydrogen atom transfer energy to an acceptor. That energy has to go somewhere, and it's received by causing ionization of the electrons of the acceptor. It has to be a perfect energy match. And what we've done in the intervening year is built upon a breakthrough that I announced last year, and that is that we found a way of making this reaction where the energy goes from the hydrogen atom to the acceptor at an extraordinarily high rate, explosive, violent rate. And that energy is released predominantly as light, and it can be converted into electricity using photovoltaic cells. What we've seen is signatures of soft X-ray coming from our cells, and anyone who's been in our lab has said that it's impossible to get soft X-ray from hydrogen. It's not known in the spectrum of hydrogen as it appears in textbooks, and we can show it on demand. That proves that hydrogen can form more chemically stable states. Those states match the signatures coming from dark matter. This ring is a ring of mass that's bending light from other galaxies. And you can't observe it. There's no visible light being absorbed or emitted from that ring. Yet it's massive in its gravitation, and you can, with very special spectrometers, see the creation of this type of material, this matter, emits soft X-ray. The same soft X-ray we're getting from our lab, and it's very strong evidence that the dark matter of the universe, which makes up 90% of the mass, is yet unidentified, is hydrogen. Essentially everything else you can see here is hydrogen, and what we're claiming is the unseen part is hydrogen as well, but in a new chemical energy state. And we've got an enormous amount of data now accumulated to prove that. Moreover, we can show analytically. We run typical chemical analytical tests in our lab. There's about 12 of them that we can prove this new state of hydrogen. We have a number of analytical tests that show overwhelming evidence that this new state of hydrogen exists and can be identified in the lab. So what we've done is harness this manifestation of extraordinary high-powered light. And you can see here there's an enormous bright flash of light. And what's interesting here is it's glowing after all electrical field and all energy has been removed. There's no energy coming into the system after it ignites. So this thing ignites, and ignites at billions of watts per liter. That's 1,000,000 times higher power density than the internal combustion engine, for example, which is the most powerful system for producing, harnessing energy on the planet. We subsequently designed different systems to make that blast, that enormous blast, a release of energy on a continuous basis, or at least a point where it's semi-continuous to the point it fuses and you're getting continuous power. So all systems have a source of electricity to ignite the fuel. They have a photovoltaic converter that convert that brilliant light into electricity, and then they have a fuel regeneration function in the systems. And this is showing. This is just, I'll just show this grammatically because it's very, very different what we're doing now in terms of final engineering systems. But there would be electricity that would run a very high current, about 1,000 times household current between these two roller electrodes. It would ignite the fuel, and you can see there's enormous blast of light that comes out. It's tens of thousands of times the sun intensity. And then we have a way of converting that light into electricity with the photovoltaic cell. Then the fuel is recirculated back into the regeneration chamber. It's rehydrated and makes a complete loop. So the fuel is a highly conductive matrix. It holds water, and the source of the hydrogen is in fact water. There's a material that produces a catalyst that accepts that energy from the hydrogen atom and allows it to drop down to this hydrino state. So it's all self-contained. The only thing being consumed in this system is water, and it's making 200 times the energy of burning, but using water, not hydrogen, as a source of hydrogen fuel. Because you're getting such enormous energy gain, you can actually use water as a source of hydrogen. So that alleviates any necessity for having a hydrogen infrastructure and going into a hydrogen economy. So this is a vehicular application. It would be the same as in electric vehicles like your Volt, Leaf, and Prius, if a hybrid, and Tesla. You'd have control systems, you have electric motors, but it would have this very, very tiny cell that uses water vapor from the atmosphere to acquire the hydrogen fuel to drive the system. At enormously higher power density and essentially infinite range, because you can pull water vapor right out of the atmosphere. Even if you used water from a tank, you're taking the Tesla S, for example, it has a megajoule, 1,000,000 joules per mile. That's their rated consumption of energy per range or for distance. And this reaction to form this new state of hydrogen releases 50 million joules of energy per mole. There's 55 moles of hydrogen in a liter of water. That translates into 3,000 miles of range for the Tesla S using water as fuel. So just to give you an idea, we feeding a very trace amount of fuel in vertically here and then running the current between the two electrodes. And you'll see that you get a very, very bright light coming out of that. So the idea is you take an intermittent process and you make it continuous by dropping fuel in there and feeding it more or less continuously. This is sped up a little bit. And then we would use conventional solar cells. In particular, there's a concentrator solar voltaic technology that's being deployed at tens of megawatt type scale as we speak. It typically has 3 layers of material, photovoltaic material, that take the spectrum from different regions of the electromagnetic spectrum, as I'll show here. So these are different types of material used on these photovoltaics, so you can cover the entire spectral range. We're working on designing specific ones for our cell, and you can see here this blue line is the spectrum of the spectrum of the sun, and the red is the spectrum of our cell. So you can see the sun and our cell have similar spectral emission, and therefore we can use known technology to convert that into electricity. So this is the first generation where we took these very energetic blasts and we took the light, used photovoltaic panels, converted that into electricity and ran a diode lighting array. So the idea is you have a big blast of light produced, and then if you do that sequentially, then you can get a more or less fused emission of electricity and run some standard load like a lighting load. One of the modifications we had to make in terms of our light source relative to the sun is it's tens of thousands times sun intensity. So we have a way of splitting the light, and that is taking the light and downgrading it across a panel of photovoltaic material. So we use beam splitters or photovoltaic dichroic mirrors that would take the light and break it into as you can see here, break it into different intensity modification along this channel. So we'd have 10,000 suns come in here, and at each level this mirror would reflect partially some of the light, and then other light would transmit up through, and we'd diffuse that light over a panel to be congruent with the existing capability of photovoltaic cells. The maximum photovoltaic cells can do at the current time is about 10,000 times sun intensity. What we're planning to use is about 1,000 times sun intensity, and using what they call a single junction versus triple junction, which the engineers anticipate about 30% conversion efficiency. This is the specs on a 10 megawatt system. We would run 25 million watt electricity. Even at a 25% conversion efficiency, we would then get 10 megawatts of electricity, or excuse me, 40% conversion efficiency, we get a 10 megawatt of electricity. That's a rating of commercial triple junction cell. The dimensions of that would be about a meter by half a meter by a meter high. So about a cubic.
Bigger than what the dimensions of that slide are. Who could see that?
Well, I'm reading to you. I'm telling you what it is. So it's about a cubic meter for a 10 megawatt scale using 1,000 sun photovoltaic converter, solar panels. If you go 10,000 suns, that would be 1/10 that size, or 0.05 cubic meters, which is extraordinarily small. To give you an idea, the internal combustion engine is about 250 kilowatts. This would be 10 megawatts at about a cubic meter scale. So it's a phenomenally high power density, very lightweight, and it's direct conversion electric, so you can run this, run electric motors with this. Yeah, I'm gonna. The main issue with that kind of high power density is thermal load. So you have this is from Azure Space, which is a German photovoltaic company. This is actually the heat exchanger on the back of the solar panel. This would run at 1,000 suns, about 40% efficiency. So this is a commercial product. So they're already rated and they're already operational to run that high a power density. What you're seeing is a very, very high power release of the water vapor in that material being converted into this hydrino form of hydrogen, being released as light. The pressure above atmospheric is very, very small compared to conventional explosive type pressures. So we've been designing fuels so you don't get a shock wave. You do get some overpressure. It's higher than atmospheric pressure, but the amount of energy in it is very, very small. So that was one of the impediments we had in terms of engineering, is how do you get this enormous high power release without really destroying the electrodes, and we've found a way around that. We've designed a fuel that makes very, very minimum shock wave, and we've designed a system where we have very low impact of the fuel or contact of the fuel for a period of time where it causes any kind of damage or degradation due to the pressure wave. Oxygen we vent. So we end up with the water being converted into hydrino form of hydrogen, oxygen, and power. Particularly almost all the power is in the form of light. Like even if you look at a halogen light bulb is 90% light, and then there's some convection of heat at the ends where the electrical connectors are. This is essentially all optical, and the optical is particularly designed to be in the region that is compatible with photovoltaic conversion. So very little pressure volume, very little shock wave, very little heat. It's essentially all light.
No one will object to adding hydrogen.
What's that?
No one will object to adding hydrogen.
You can add hydrogen in the chamber. You can do electrolysis and permeate it through a semi-permeable membrane, and then the hydrogen go in the chamber. Again, the amount of fuel consumed is very, very small. It's 1/200th the comparable amount of hydrogen you would burn to form electricity, say, in a fuel cell.
Is that pure oxygen?
It would be pure oxygen. And the atmosphere actually is depleted of oxygen. It's actually lower in Philadelphia than it is out in the suburbs because of all the combustion occurring to maintain the predominant source of power in our economy, which is combustion in automobiles and coal and gas power plants. So this is these are other examples of commercial solar panel materials. This is talking more about the dichroic mirrors that we'd have on the photovoltaic panels and split it. So we can use single junction versus triple junction because we uniquely have a very, very high light intensity. This is showing another PV application here. So what this is about is we had before single pellet blast. They were making on the order of 1,000,000 watts of power, but they were very, very short in time. They're only a thousandth of a second. So the idea is to run fuel through and make it continuous. So you have continuous light output and make continuous electricity. So this was an early version we did back in July. And since then, we've totally revamped the system. It was a matter of getting, if you have a thousandth of a second pulse, you have to get 1,000 pulses per second. And we've achieved that. We have engineering systems that will do the fast enough electronic switching that we can do 1,000 pulses per second, very, very high power, fuse the light output, and produce electricity continuously. So then we'll look at the economics of that. What we're showing there is about 27 watts of LED lighting. That was July of this past year. And there's a lot of levers we can pull the very vastly increased amount of light and thereby electrical power. We can go much wider on the rollers. We can go much higher on the frequency. We can go feed fuel through at a higher rate. And we get to some astronomical numbers here in terms of millions of times higher output in light relative to what you saw there, just by very, very minor modifications of that base system. And that's what we've been focusing on. How to make an engineered system. So where we are right now is, as I said, there's a source of electrical power that ignites the fuel. There's a converter that converts the light into electricity. There's a system that feeds the fuel into it as part of the ignition system. And then there's the regeneration system. All those systems have been engineered, and they all are shown to be operational at the type of rate that we need in terms of feeding the fuel. So if we can fire 1,000 times a second, firing it 1,000 times a second, recovering that, reprocessing the fuel, and then resupplying it, we can do that 1,000 times a second. The photovoltaic converter manufacturers are saying they want to go single junction. They think they can get 30% efficiency. They want to go initially 10,000 suns, but they're going to go 1,000 suns as a first generation system. And it should be compatible with everything we built in terms of our light source. We're shooting to do 300,000 watts of light at a 30% conversion efficiency. We're looking at about 100,000 watt electric is what our objectives are for our first prototype. Then we're going to make a modular, scalable, 250,000 to 10 megawatt unit. So it'll be the same base unit. It'll have the same controls. So we have the software written. We have the control electronics done. Different parts of the mechanics and the electronics to run it, and we're trying to integrate all the systems so we have a 100 kilowatt electric power system. So to coincide with that, we're working on setting up the various businesses offices. So the model is to have OEMs manufacture, and then we would lease the equipment to distribution companies. And then we would do revenue sharing on the revenue from the different applications. So to give you an idea, if you take traditional solar and you'd say, well, solar seems kind of expensive, but not when you're 1,000 times sun or 10,000 times sun. So let's say it's $4,000 a kilowatt installed. That becomes $4 a kilowatt installed at 1,000 times sun intensity. And it becomes even 10 times cheaper than that if you're going to 10,000 sun intensity. So it can pay for itself very, very quickly. So that's the advantage if you're looking at these PV costs. So we found there's basically a cost. There is no fuel. We're using water. The catalyst and the other components of the materials that go in the fuel are used over and over again. Yes. So that's basically it. To give you just one model in terms of if you go stationary power, this is a megawatt unit. It throws off about $1 million a year revenue at $100 a megawatt hour or 10 cents a kilowatt hour. One thing that we've looked at is very interesting in terms of breaking into market in a very big way. if you look at, I know fuel costs have come down, but let's say you take, just for a typical vehicle, like an F-150 Ford pickup truck, which is the biggest, probably the top selling vehicle in the United States. You're looking at a couple $1,000s per annum fuel costs. So let's say you put this unit in a vehicle, so 100 kW, that scale is enough to run a vehicle. What we're shooting to make as a first generation would be enough to run a vehicle and be compact and can run a vehicle. The PVs are rated 25 years. The electric motors are like a 10-year warranty. Everything on it should have a very, very long longevity. And very, very low capital cost, infinite range, extraordinary power compared to conventional internal combustion engine, for example. So let's say you get $3,000, or just throw a number, $3,000 a unit per annum fee for that vehicle. 60 million vehicles made per year. So you multiply that times 10 years, at 60 million vehicles, at $3,000 a year, it's $1.8 trillion a year. And then you use the vehicles to charge homes, businesses, and the grid's gone. So there's avenues, and that's not counting freight, which is continuously running the power source. If you ran 10 years and you're just doing $3,000 a year in fuel costs, that only translates in about 3 months of continuous use. So you can see if you're doing it continuous usage and you're doing all the other applications, then you get into freight and you get into marine and you get into aviation, it just becomes extraordinary the amount of revenues you could proliferate with this. So our goal is to enable the business community to use it, have OEMs manufacture it, get it out in the field, and then do revenue sharing with those businesses that would deploy it in such a manner. Okay, any questions?
How far along with manufacturing capacity? How many of these things can you make?
Well, the engineering firm we're working with now said they could make $1 million a year, and then their sister company has 325,000 employees. They said they could make millions, many millions per year of the several hundred K. What's that?
How has it been funded today?
We have various investors. We have hedge funds, some companies, and private wealth. We just did a round. We were going to do a round in the summer. We closed July 31st for $10 million. Actually closed at $16 million, and we had more investors that wanted to come in. We're trying to convert those into licenses now, distribution licenses. But we were well capitalized, and right now we're just integrating all the systems. And once we get all those systems integrated, we're going to put the photovoltaic conversion on, and then we should have a unit ready to show the world. So we're working on setting up business offices around the world simultaneously with the development of the power system. We think once the power system is available, there'll be enormous demand, and we want to be prepared for that.
Is there a proof of concept design already? I mean, is it there? Is it already out?
Well, if you want to know proof of whether you can make a new state of hydrogen, there's 12 analytical tests, and there's soft X-ray light, and there's enormous amount of astrophysical data, enormous amount of theory, and there's specific power tests that we've run, and universities have run, instrument manufacturers have run, and they all say there's unequivocal power. There's no question. If you're interested, within $100 and half a day's worth of scheduling, you can convince yourself absolutely that there's power coming, or there shouldn't be power. Then beyond that, we're engineering things. You can clearly see there's a blast. We're taking high-speed photography that you're seeing that there's an enormous amount of light and power being released even when there's no power going in and there's no chemical reaction that's possible with those fuels. And then we have specific engineering systems that show that it really does work, that you can ignite this fuel sequentially and fuse the light depending on what frequency you do the ignition.
So when do you get a prototype that can maybe not do 100% of what you expect, but even a 10% gain is a significant savings, right?
Yes.
So when is that? How far away?
Well, we have all the systems tested. I was saying we've tested all the systems and showed that we can operate at that 1,000 hertz.
Do you have any of the videos?
Well, I showed the high-speed video, and some of the videos of what we did in the summer. So, and that July demo in the summer was to show that you could You could use a rotary pump to suck in the fuel and supply it in a semi-continuous to continuous manner, and then we've optimized it beyond that to go much, much higher light intensity and in an engineered design that's more commercially practical and applicable. That was just kind of show proof of principle that you can inject fuel into it and make it continuously make light as you injected fuel in it at the same rate. Yes?
I think you hit on a couple areas, but what are your top market sectors that you're focusing on initially?
Well, we've had people that have approached us, and we're working on a deal. We're getting pretty close in Mexico for heavy industry, and we're working in Canada in terms of buildings, doing larger scale buildings like office buildings and malls and the like. And then we think data centers is an interesting market. We're looking at that. We have some interest in that, and we're looking into that ourselves. If that doesn't come to fruition, and then certainly the automotive market is something that we've done some conversations. We've got a big auto parts manufacturer. They do about $40 billion a year business. They said they want to get into the business. So once we get our integrated system, we're going to start negotiating with them for automotive. I think automotive is a nice sweet spot. As I was saying, the numbers can proliferate and be really big very, very quickly. And then we have some utilities that are negotiating with us and continue to stay involved with us because they're interested in the unregulated side of their business and getting in early on.